for me, it's an honor to be part of the GeoVia Connect 2025, where I'll be doing three presentations. And the first one is to describe our mine planning and design tool for mine caving operation with Surpac. This presentation is divided in 5 parts. The first one is related to the history associated to our caving tools. The second is a description dedicated to block caving, and the third for sub-level caving. And in the end, we're going to be doing the takeaway, and we're going to have some time for questions and answer. So our history, it's quite extensive since start more than 30 years ago when the first version of PCVC was developed in those, so as you can see here at the left. That was our first opportunity to start doing mine planning for block caving. And that was evolving in the solution that most of you know in GEMS, because that's part of the last 20 plus years of development. That include not only tools for block caving, since in 2007, we developed PCSLC dedicated specifically for sub-level caving. And also we incorporate some tools for footprint finder, early stage in the project, or even for daily or shiftly operation. Now, 2 years ago, we isolate the IP, the caving IP in GEMS, and we migrate that into Surpac to provide, longer future maintaining the same engine that we use in GEMS, but now running in Surpac and taking the advantage of all the benefit that is included in Surpac, like running with 64 bits, providing better performance and modern graphic. The interface that was developed to connect the previous IP, it's simpler and more user-friendly. Also, we have much better help files and assistance. So for new users specifically, it's going to be simpler and easier to learn how to work with this tool. Additionally, Surpac support multi-language, so it's accessible not only in English, also in Spanish, Chinese, and Russian. So it's more applicable in other geos, facilitating its utilization. And also bringing a powerful and very flexible scripting engine to automate any function or any workflow. We're also proud to say that due to this long history and legacy for more than 30 years, we are currently the most widely used software for mine planning and scheduling of block caving mines and projects. And as you can see the dots in the map, we are nicely distributed worldwide. So you can see in green all the our existing install base, but also we have been working in many projects in other places as well. And you can see the long list of user at the left where you can recognize big companies. So we're very proud of our install base. Now, let me take you to the mine planning tools dedicated to block caving. For that in Surpac, we have different roles that can cover widely from early stage of a project, block caving project, going through every single aspect of the mine planning up to the operation. So it is indeed a compelling solution where you can start with, the block model to do initial economic analysis then adding the inputs and assumption that you needed to select and run a strategic analysis to define what is the optimum elevation for a block caving footprint, and also defining what is the size, the optimum size of that footprint according to certain inputs and assumptions. Once you have that defined, you can run a number of sensitive analyses in a short time. Then once the decision in terms of the extraction level location and the layout that you're going to be using, you can start working in more details by using our layout and design tools to distribute the draw points and start creating the model in detail that can be done even per draw point. Once you have that, you can start utilizing all that level of detail into the production schedule and even during the flow modeling analysis. Also, we have some product schedule optimization tools that help you to add operational constraint and generate a production schedule that meet all those constraints. And in the end, we can move into the daily operation. So what you're seeing here is a project that you can take from the beginning when you do all the strategic decision, then start working in any level of detail, yearly, quarterly, monthly, and even in a daily or shiftly basis with our production tools. Now, at the beginning, you can use our cave footprint finder role to do strategic analysis and answer critical questions like what is the optimum elevation for the extraction level? And for that, you work directly with the block model, and that simplifies the analysis by, for example, setting one specific level. In that level, Footprint Finder will generate one column that mimic, what is going to happen in a draw point. And by building that column, we apply some mixing parameters, then economic analysis to define what is the optimum elevation according to those inputs. And you can even use a clipping polygon to limit the area where this analysis is going to be done, which is going to be important for certain deposit. This video will show you how Footprint Finder works, so you can have an idea about the block model distribution, the clipping polygon that in this case covering the entire block model. Then you can basically define in one interface all the inputs and information that you're going to be using in this analysis, including the list of elements that you wanted to model and all the specific inputs that are required for a proper block caving evaluation. When you run, the system simulate for every level the extraction of a block caving mine. So even applying or using a simple production schedule. So you can see here even very quickly how the sequence is working, moving from the center to each size. The lines represent the height of the draw column or the economic column. So it's giving you an idea about the volume of the area that is being extracted level by level. Obviously, when you are going up, that volume becomes shorter because it's closer to the surface. By doing this, you can apply numbers of inputs and parameters and run numbers of sensitive analysis. So you can easily understand how sensitive some of those parameters could be. The results are directly dumped into Excel, so you can see what is the value and tons extracted for every level. And even for each level, you can see the detailed information for the production schedule simulated. So you can see here, for example, for that case. Now, this option is not only for one specific footprint. It can be done and cover, I, uh, I can say, for any block caving or panel caving operation. It could be a multi-leaf operation, or it could be an incline cave, or even in some cases where you're going to be working not only with a large unique footprint, so you can define, for example, splitting this into two areas when you do the analysis. Where is the optimum or the partial optimum for two different elevations? And in other cases, you can even incorporate material that is being extracted already as a residual model on top, and seeing how much of the ore is being remaining there to affect the decision where your optimum could be defined. Now, after the decision of where is the location, the optimal location for the footprint, we're going to start working in more detail. And this is where the footprint detail is relevant, because you're going to be creating the slice file by combining information from the block model, the draw point location, and the draw point geometry. So we do have the tools to generate different layouts in different um, forms, and easily adjusting the parameters to quantify the impact of having, for example, a larger pillar or different distribution, or even a different layout type. Once you have the information created as a slice file where all the information from the block model is distributed per draw point, you can do more detailed analysis. For example, defining according to the economic limits, what is the optimum size and shape of the layout, even using some geotechnical inputs to constrain that. Also, you can run multiple production schedule with number of alternative in terms of the level of detail that you wanted to review. That can be done by year, by quarter, by month. Everything depends of, how big is the period that you want to simulate in this case. What you're seeing in this video, it's a production schedule done, but also using some of the complex flow model that we have, in this case called marker mixing. So you will see a vertical section of the draw points in here, and how the extraction start according to the sequence, and how the K-back is growing, generating some air gap and lateral movement around. And once you break through the surface, you can see external material with black color entering and being mixed with the ore associated to that deposit. So it's quite a complex mixing model that can model most of the elements in a typical flow model for a block caving mine. As you saw for Footprint Finder, also the result is done automatically to Excel. So you can see period by period what is the result of your production schedule, where you can quantify, tons, grade, and any information that you wanted to track by period. But also, you can have a number of other detailed reports, even per draw point. So you can get a lot of good details with that. Now, another important aspect is the flow model itself. And if you have some actual data or some monitoring system, for example, beacons, you can compare those beacons that are in these red circles with the extraction that you're doing in those simulations, and see how the beacons are moving in reality, and how you can mimic those behavior according to the flow model parameters. You can have a lot of different options in terms of visualization. For example, here, those um, little discs are representing how the K-bag is growing, but also you can associate the original position of those beacons with the draw point allocated. So you can see if you're having a lot of lateral movement or just straight, vertical movement. So it's a lot of interesting and very helpful visual information that can be used in this case. This is just a quick view of where we can do in operation, but basically, this is taking the information that you are working, in a longer period of time and start seeing as an objective how much can be extracted per day or per shift. And this is taking a whole new level of consideration. For example, the availability of the draw point, the status of the draw point, where is the production target, what is the priorities that you wanted to have. And also, you can connect that with your dispatch system or even with your automated control room. So we can interact with all those elements back and forth to send the next uh, draw order or receive the actual information to update, you know, in a shiftly basis or a daily basis where you are within the month. Now I wanted to share with you, the same tools, but that can be applied for sub-level caving. Because the interesting thing that we did in Surpac was having the same roles, but can can be used for both purposes. One for block caving and now for sub-level caving with the specific tools. For example, following the same logic according to the project life, we start at the beginning with the block model, but we can use the footprint finder to define, not in this case, what is the best optimal unique elevation for a footprint. In this case, we're going to be evaluating what can happen with the sub-level size that you are choosing and doing the economic evaluation according to all the complexity that sub-level caving has in terms of extraction and dynamic dilution. With that, we can run also a number of sensitive analysis. And once you have the limit of the layout and footprint per level defined, we can model everything in detail per ring and run production schedule, also use our flow modeling tools, and even adding some operational constraint in all these analyses. As I described for block caving, footprint finder has two components, one for block caving and the second for sub-level caving. So you can run the analysis, but again, taking into consideration the complexity of the distribution of different levels and also the dynamic condition of the extraction and dilution that is taken according to a specific sequence. And for that, we're going to be seeing this uh, video where you have the block model. And according to the level size, it's creating a composite that is replicating, the extraction per level according to the reality. And for that, you can have this user interface to specify, for example, mining cost, metal price, what you wanted to report, but also specific inputs that can be provided directly from Excel. In this case, simply the definition of the level according to the level spacing. How is the sequence going to be applied in terms of the shape and the origin? And when you run, you will see all the result in Excel, but at the same time, you will see a graphic representation of the extraction from top to bottom. So you will see some coloring here. It's quite fast, but then I'll show you how you can describe it in, a different way. But what you're seeing with this flashy color is basically the simulation of the extraction for those levels in a sequence that is taking into account, how many levels you have actively working, and also um, what is the shape you want it to have? What is the connection that is normally constrained by geotech between levels and so on? When this is when this is completed, you can have a 3D representation of that, or you can visualize the result directly in Excel. And here is quite interesting because it's not only reporting tons and grade per the entire ride. Also, it's having a description of how much was extracted per level, so you can have a better understanding of the distribution of the material and how it was extracted. And as I mentioned before, the visualization was quite fast. So automatically those pictures are being generated. So you can review in detail, how many levels you have active, what is the angle that you are using to control the offset between level. So even though it's running in the block model and using a lot of general assumption, it can give you a very good shape and idea about, for example, the sequence and the connections between level. With that information, we're not only considering what is economically extractable per ring, per level. So as you can see in this visualization, we can even use a 2D offset to see what is the distribution of the positive economic area per level to identify and limit what is the size of the footprint for each one. But sublevel caving is more complex and tricky than that, specifically when you have not only a vertical distribution in the ore. When you have some inclination like this, you need to do some further analysis, for example, for those rings that are directly connected to the dilution. So probably you want to extract less. And since those are connected vertically, and whatever is not extracted in the top level could be extracted in the level below, and try to recover as much as you can from the footwall in this case. So we have, in this case, some options to run multiple iterations to optimize your draw strategy, your extraction per ring per level. So it's quite nice and sometimes provide a very interesting and encouraging result. For example, here from the base case to the last iteration, the tons was increased by more than 10%, and the overall value as well. So it's very helpful. Now, when you have the definition of the limit of the footprint, we also have some specific tool to help you with the design. So we can generate those tunnels automatically. And once those tunnels are created, we can divide those tunnels according to the burden or the ring spacing to generate the distribution of the ring. Then transfer the information from the block model to each ring. So that means every ring will have a specific information associated to the block model that can be used after once we start simulating the extraction and the mixing associated to that. As you can see in this example, we have 11 levels, almost 900 tunnels, and more than 26,000 rings. But we have a good experience, and this tool is capable to do even up to 100,000 rings with no problem. So it has a lot of benefit in that way. Now, the second part of this is the generation of the production schedule. And for that, we have specific tools to work with the mine sequence and get the tons target and then the specific information, and obviously combining with the ring model that is created in the previous step. But additionally, you can apply some specific inputs to define your draw strategy. For example, using not only the percent of extraction to close a ring, also we can use a shadow gray that can be even variable to have different strategies. Once you combine all those elements, you can create your production schedule to know where the material is coming from according to the extraction for different levels, and also reporting, tons and grade accordingly. This is also associated to the mixing, and this is another example of one of our numerical modeling tools, where you can see clearly how much material is being extracted per ring according to the rules that manage the sub-level caving extraction. And for the dilution, you can even specify different um, type of source and flag it differently, so you can track those dilution differently in the model. And once you complete the extraction according to your strategy, you can even evaluate graphically and numerically how much of that ore is being remaining or left behind. So this is something that you can do also for the block cave. Once you complete the extraction here, you can convert whatever is left behind as a remaining material in a block model. Then you can use that for future evaluation if the deposit, continues vertically. Uh, so you can have that combination for future analysis. And once you complete the production schedule, the level of the report can be done by ring or the total, where you can see clearly the tons and grade and any material that you wanted to uh, report and bring from the block model. But also, you can track how much was the extraction and where the material is coming from. So initially, in the first period, obviously, most of the material is coming only from the level where you're drilling and blasting, but also having some external material or some additional uh, material that is not part of your design, is coming from outside as part of the flow model component. So it gives you a really good idea about the mixing and combination of the material that you are evaluating. Now, if we talk about the benefit from Surpac, the option to use a scripting engine, it's really helpful. So the thing that you can do, it's you can record any macro to run any function just by starting, the recording, then run on a specific function where all the inputs and parameters will be saved and stored in a text file that you can even change that after and run it again. So what that means, you can just record one specific function, change some parameters, or run it again to generate whatever you wanted to do. Or you can start connecting those macros according to different steps of the workflow to automate the entire workflow. In this example, I managed to create, record individual step, for example, the layout generation for an SLC project, then the creation of the rings, then the transfer the information from the block model to each ring, and finally the connection of the ring between them. So we can easily automate the whole process as you can see it now, even creating after the model it's been constructed. You can even run the sequence as you need it. So you can start a project by changing geometrical parameters up to the generation of a specific production schedule to quantify what is the effect, for example, of changing the geometry in terms of level spacing up to the result directly reported by ring and in a production schedule. So that is an amazing tool that facilitates to do a lot of repetitive work. And I would like to share this example because this is where we start using for a specific objective. In this case, we were working in a project, and the first objective was to maximize your recovery. So we built this footprint that tried to extract uh, most of the ore economically extractable. And then when you apply some specific draw strategy, we were happy. But then, and we were happy because we were reporting more than 100 million tons, which represent a good ore recovery. Now, according to that strategy, after running some financial model, we see the result. And unfortunately, we were not that happy because obviously it was a negative MPV. So then we started making changes. We didn't change the shape of the layout, but we start working with different shadow grade, shadow value to start having a better extraction profile. With that, um, basically we start, you know, restricting the top level to be able to get better grade from the top and closing some of the ring earlier, and then try to capture that remaining ore in the level below. And it was good. We obviously sacrificed some reserves, so the result went down to um, almost 100 million, a little bit more than 100 million, and the NPV increased, but not enough. So then we start doing, you know, a more serious consideration in terms of the strategy of the variable shadow grade without changing the layout shape. So we start closing draw point, you know, more aggressively for the same shape, and the results were encouraging. We reduced the reserve, but the NPV result increased. But then we realized that the investment to build the whole thing is quite expensive. So we took a different approach. And for that, we automate the workflow. And we start testing different options, not only um, seeing what is still economically extractable and using the variable shadow grade, but through that type of analysis, we discovered that we can start shrinking the shape of the layout by working with an iterative process and is automated or semi-automated with the macros. Um, and finally, we got a smaller footprint, but given us a really good result. So the first model um, moved the NPV over $1 billion. So going from a negative to 1 billion was really encouraging. However, this sacrifice that we made in terms of reserve was quite high. So then we, you know, relaxed some of the constraint to improve the ore recovery, and we move it up. We're still working in this project because we want to see if we can move to this quadrant. But the amount of work that we did in a very short time demonstrate the value of automating some of that process through the macros. So now we're almost in the end of this presentation. So let me summarize some of the takeaway. In general, where we're seeing with this tool, it's allowing us as a mining engineer to design and plan KV projects on mine to enhance the result, and also providing very quick result for production scheduling and flow modeling tools. And if I have to translate this and simplify in probably 4 points, it's the first one, it's the time saving. We are seeing an increment on the time of the process up to 5 or even more times when we're running now due to the 64-bit and multi-core processor. Just to give an example, in some cases, when we are running production schedule in detail with more than 200 periods, that take previously 30 minutes. Now it's taking 5 or even less minutes. So you can run more iteration and do more analysis with that. The enhance of the usability. it works with a mass user interface, multi-language support, and the help files and assistant. Um, it's really helpful, specifically for new users. And the model visualization is fantastic because as you can see in this video, you can even split the screen in two and have two type of visualization when you are doing some analysis or highlighting things, in the evaluation. So it's quite powerful and modern um, now. And finally, as I showed you a couple minutes ago, the workflow automation. It's a fantastic tool, very powerful, and we're exploring more tools to evaluate different options with the same tools that we all love. So I hope you enjoyed this presentation.